Hi guys. Can anyone hear me? Okay. Yep. Thanks for coming to the first database workshop for Orbital25. Um, yeah, there was an unexpected schedule, which I apologize for this. For the next workshop, it would be the same time, which is 10 a.m. and it won't reschedule anymore. Um, so without wasting too much time, let's get started. Uh, can you see my screen? Okay, thanks. Yep. So, welcome to the first session for databases. In this workshop, we would introduce basic concepts of a database, what is SQL, and we'll do a demo in PostgreSQL, which is a very popular open source SQL database. Yeah, I think the waiting room is like, I'll give another like 5 more minutes to admin. But we'll continue right now because it's already like 3:05. Yeah, so there's actually a lot of things to cover in terms of the topic of database, but I would deliver enough content for you to understand like how to get started with a database for your Orbital project. Um, you would understand enough to um, be able to get started on your own, be able to learn it yourself because you already have the foundation. Um, so for me, so today's plan is database concepts, core SQL concepts, PostgreSQL demo and hands-on, and a wrap-up. For this, we have a Q&A session, and also next steps, which is like a brief overview of what we are going to discuss in the next workshop. Yeah, I don't really have an intro slide. Yeah, so my name is Yin Joe, currently a year 3 computer science student at US. So we enter the topic of like what is a database and why do we even need a database? Why not just like store it in your own code? Like you can just have a data structure in your code and store everything that you need. Uh, so database is an organized collection of data managed by a DBMS, database management system, that interfaces with users and applications to store and retrieve information efficiently, which is very important because the amount of data that we can potentially have can be up to billions of rows, uh, and there will be several hundreds or thousands of gigabytes in terms of storage. And database systems ensure data integrity, security, and concurrent access control, which is basically an abstraction of all these very important aspects of building a data, having a data storage for your application, because basically you want to make sure that the data is integrity means that the data is stored is not corrupted. For example, let's say um, how do you organize different types of data uh, of your application, and how do you ensure that uh, over time this data doesn't decay into something else that doesn't actually represent what you want. And of course, security is very important because you don't want your customers to be able to see the personal details of your other customers or something like that. You don't want to lose your customer data, and you want concurrent access control because let's say uh, we are running a large scale application nowadays, and let's say you're using TikTok or you're using Instagram or some other application that has a large amount of users accessing the data at the same time. We want to ensure that everyone gets a chance to access their own data so that we don't slow down the entire application and affect everyone's experience. Uh, so why do we need a database? It's because of all these abstractions and also the need to store data. Because basically, uh, in modern applications, like you have learned in your CS courses, uh, we basically have different uh, in your any computer system. Uh, we basically have tiers of storage. So the first tier is of course uh, your register, your register and CPU, which is maybe 32 or 64 registers only. These are extremely fast. It can be fast, even hundreds of times faster than a nanosecond every time they do an operation. And then the next tier is uh, your L1, L2, L3 caches, which is also in your CPU. They have more space, but they are even slower than registers. Then the next tier is finally your memory. Uh, so your internal memory that you learn in your CS 2106. Um, this is the place where we have floors. We can have several gigs of memory. They're even slower than L1, L2 caches, but they have more memory to store things. And then finally, you have disk, which can be up to thousands of gigs. But they are, compared to RAM, compared to in memory, they are extremely slow, but they can store a large amount of data, which is very helpful for your actual needs of your application. So a lot of times, the bottleneck of any application is actually like how often do we make use of the levels that are on the top. So for example, if your catching is very efficient and you always hit your catch in your L1, L2 or memory, uh, and you use lesser disk, then this can greatly reduce your latency and the amount of time you take to retrieve data. So of course, in real life, we have billions of rows in data, and we definitely need to use disk. But even if we use it, so that is why precisely why we can't realistically expect to store everything as data structures in your own programs. Um, so you need to actually store this data in a disk, but when you retrieve it, you want to store it in a format that is extremely efficient to retrieve and minimizes the amount of disk operations that you need to make. Yep, so that is an overview of why we need databases instead of just storing everything in memory. Yep, so of course there are different types of databases in existence. One of them, which is probably the most commonly used ones, are relational databases. Um, So relational databases store data in tables of rows and columns. So they organize different categories of data into tables. Uh, and for each table, for example, all our customer info is stored in the customers table. And we have rows and columns similar to your Excel sheet. And we want to enforce schemas and relationship through keys, which will be discussed later. But basically, schemas is like what you specify. For example, what columns do I have for the customer? Maybe the customer ID, the name, the age, the gender, and so on. You want to enforce that every time I insert or update data, every single row in my database should, on this table, should comply to the schema that is defined before. This is to maintain the data integrity. So you won't have situations such as you want to retrieve the age of this customer, uh, but when you retrieve the database, you can't find the age because it's blank or it's null. Uh, we want to avoid such situations. So in the schema itself, we want to specify that this field should not be null. Otherwise, any other insertion that violates the schema will actually fail. So there's also this concept called ACID properties for only for relational databases. This is actually slightly more complex in terms of the concept itself, but I will briefly explain what each of this actually means in the context of a database. So for atomicity, this means that any operation is any database transaction or operation is either one or nothing. It's either all or nothing, which means if you try to insert something into the database and it fails, uh, then the database state will not be changed. And if it succeeds, then the state would immediately switch to a new state. And there's no in between. There's no like partial. Your operation is partially in the way, and suddenly someone else interrupts it. And uh, of course, that will cause a lot of issues. And for consistency, also there's a lot of definitions of consistency in the context of concurrent programming in a database. But what it basically means is that any operation that you do on a database, even though if you do it concurrently, multiple users try to modify or read something from a database, uh, the sequence of the operations is always consistent. So you wouldn't end up in a state where, let's say this database is for a bank, and you wouldn't end up in a state where you can withdraw money that doesn't exist, or you can store uh, you store some money, but when you try to retrieve your balance, it isn't there. These kind of situations will not exist because of consistency. And for isolation, um, basically, uh, every transaction or operation is isolated from one another, which means they will not affect each other. Um, and then durability means that because of the underlying infrastructure that we use to implement a database, for example, disk or even like memories, some of these are not completely reliable because they are bound to failures. So, for example, the disk might be stuck or something, and the whole database would fail. Um, so when so this is inevitable, but problem is when it fails, we always have a mechanism to back up our data. So to always when we restart the database, it will always arrive at a state where we can reconstruct the operations that are not yet stored into the database. So we will never lose our data, um, no matter uh, when it fails what or what part of the database has failed. As long as we restart, we'll have a way to restore the entire database. So that's for durability. So because of all these properties, this guarantees a very basic guarantees that in a production system, it would a database is reliable abstraction or reliable software to store data. So of course, apart from the previous relational database that we have discussed, there are also other database models. For example, NoSQL, graph database, and vector database. So for NoSQL, there can be multiple types. For example, document database, for example, MongoDB, and key value database, for example, Redis. So key value database is basically something like a hash table, as you've learned in 2040. But this hash table is not just in memory. It's not just in the code itself, but uh, it can be in memory. But if the memory is not enough, then it would allocate your storage into the disk. And another difference is that there are multiple processors that can access the same key value database. But for your hash tables in your code, there's only your own process that can access it, and no one else can, unless you use some other like like shared memory or some other inter-process communication. But in databases, all these inter-process communications are already abstracted out. Um, so columnar database, this is basically a database that is stored in terms of columns instead of rows. So uh, so how to visualize it? Basically, in your Excel spreadsheet, you store the data row by row. So you see it as, okay, one row and the next row and so on. But in columnar databases, they store based on columns. So this column is a list of values, and the next column is a list of values, and so on. So the benefit is that if you want to retrieve just one column, you can do it very fast compared to just compared to a row-based database. And finally, the next graph database is basically for traversing relationships without costly joins, because in your social networks, in your Facebook or Insta, uh, you follow people or you befriend people, and this means that like there's like a graph like a graph data structure. There's a relation between these two people, and if you use conventional databases, it may not be very efficient to trace out the relationships between different people. But with graph databases, this can be much faster. So it's more likely used in this scenario. And then the other database is a vector database. So nowadays we have your ChatGPT or your Cloud, Gemini, and so on, all these large language models. And the underlying implementation of a large language model is basically a transformer. Um, transformer relies on uh, basically relies on vectors which are encoded from actual text. You encode the text into a vector, and then you have a vector space, which is each vector represents some kind of text or a section of text. Um, so, and then we run this models on top of these vectors. So the vectors can successfully represent the relationship, successfully model it very well, the relationships between different texts. For example, like similar phrases or similar um, text is they are very close in terms of the vector distance. So vector databases are specifically designed to store vectors, store embeddings of for similarity search or some other operations. For example, in Redis, there's also a thing called Redis vector search, which is specialized for this purpose. But the underlying implementation is still a key value paradigm. So we also discussed like the two main different scenarios in which we use databases. So the first scenario is OLTP, which is online transactional processing. This is basically it handles many small and concurrent transactions in real time, which is something like your TikTok or some your Amazon or some Shopee or this kind of applications that need to handle a large amount of users accessing or modifying data at the same time. The other one is OLAP, which is online analytical processing. So this is a different paradigm in which we don't really need to do like instant real-time database operations. So that means that it doesn't need to be like immediately consistent. Um, but this is mainly done for data analysis or data science projects where, let's say your company has, let's say for TikTok, the company has a lot of data from the users and from what the user views, clicks, and a lot of things. Basically, there is an OLAP um, scenario we use here for the recommendation systems and all this different data science projects where there's no actual concurrent multiple transactions in the data. It's more of like how do you efficiently load a large amount of data to do your data analysis, your reporting, or your machine learning. Yep. So why do we need SQL for relational databases, or even like we have SQL-like languages for non-relational databases. Uh, it is because it is a declarative language, um, which you describe what you want, not how to get it. Um, so so the underlying way of how you get the data from all the disk and all the files inside databases already abstracted away. So you only need to say what you want, and uh, basically you retrieve the data that you want very easily. And the syntax is also very English-like, and it is standardized in terms of it is an international standard, and most relational databases support SQL. Some may have different minor variations, but the very fundamental operations are exactly the same. So you can, let's say, if you learn PostgreSQL um, version of SQL, you can easily pick up MySQL, SQLite, and so on. So we would briefly look through like what kind of operations does SQL support. So it handles querying, which is like help you select or read a certain amount of data that you specified. And it also supports insertion, updating, and deletion. So basically, these four operations are CRUD operations that people commonly discuss. So C is create, R is read, and U is update, and D is delete. So these are the four core fundamental operations that we use to operate on data. And also we can create and modify our schemas using create or alt keyword. Um, this helps us maintain the data integrity of our system. So under the hood, SQL queries are optimized by the database engine. So it's very different from like, let's say you have a text file and you just read everything from the text file and do everything in memory. That works for small amount of data, but it's not scalable for like larger amount of data. Instead, they organize these files into different parts, and uh, so that we don't actually have to access all the files. And there's also cache, and there's also ways to reduce the disk operations. So it's very widely used in the industry, and it's very essential, especially if you want to be a backend developer or a data analyst, data scientist, basically engineers in general, even in other fields, need to access large amounts of data to analyze. And SQL is basically 90% of the use case. So we discussed some terminologies before we get started. So a table is a two-dimensional structure of rows and columns. Just like your spreadsheet, just like your Excel. And the schema defines each table's columns and data types and constraints. So not only the columns, but you can also define that. Let's say age is an integer instead of like text, so that you can maintain data integrity and also like avoid using too much space for something that is like actually occupies a small amount of space. For example, you want to use Boolean for actual Boolean instead of like using integer, because Boolean is just 1 byte and integer is like 4 bytes. And the common data types that we use include integer, text, or varchar, which you can specify like what is the maximum length of the text or the varchar, the date, uh, and then Boolean and numeric. So numeric is for like float values that you want to store, float or double values that you want to store. For example, for for money, and you can also specify like how many decimal places you want to track. So next we also have different. Uh, so we discuss what is keys in databases. So um, this part is different from your actual Excel or spreadsheets that doesn't have keys. So basically, a primary key is a column is added on a column to uniquely identify each table row. This is very important to distinguish different uh, different data, and it must be unique and not null. And basically, with the primary key, you can identify any entry in your database. And any single entry in your database, and also a foreign key. This is optional. Primary key is mandatory, uh, but usually mandatory, but foreign key is usually optional. It references a primary key of another table, and it enforces referential integrity. So what it means is that let's say you have a foreign key which references primary key in another table, and that the original entry in the table was deleted, then your foreign key is no longer valid. And basically, the database will also check this foreign the table where your foreign key is in, and basically raise an error, or basically it handles the situation based on what you actually um define it. So you can actually, let's say, delete the foreign key as well, or it can just ignore it. So just set the foreign key to null, and you can also do other things. So to visualize what we have right now, uh, before like jumping deeper into the commands that we have. So basically, we can organize our data into tables. So each table has its own schema, and each table usually stores the data that are exactly like the same category or type. So for example, this can be like customers. This table stores all your customer data, and the other table really stores like products. So let's say you operate an e-commerce website, and you want to store like your list of products. So maybe the next one will be like your suppliers. So it stores the list of all your suppliers, and each of them have a schema. And then let's say each product has a supplier. So there's some kind of relationship between them. So we need to use a foreign key to keep track of this. So there are actually two ways, uh, depending on where we want to put the foreign key. So initially we have primary keys for product, and of course also for suppliers. These are all unique, so you can identify um, unique suppliers and products. And and we also want to identify the type of the relationship between products and suppliers, whether it is uh, one to one, one to many, or many to many. Um, there's only like three types of uh, relationship. So one to one means like you can only relate them one to one, one on one. One to many means maybe table A has multiple table B. A has multiple B, or many is like many A's get many B's. So um, yeah, so that's a relationship. So to identify, basically your product can have only one supplier. Of course, we can also make it more complex, but uh, let's say in this case we define it to be one product has exactly one supplier, um, but a supplier can supply multiple products. So it's a one-to-many relationship, uh, and because of that, let's put a foreign key in products instead. So we have a we have a foreign key FK for supplier ID, which references supplier ID. So every time we grab this product, we can also immediately reference suppliers this to look at the details of the supplier of this particular product. Um, for example, the supplier name, the supplier company name, and so on. And every time we have a supplier, we can identify what kind of products that it actually supplies to us by just doing another query on the products database, because both have a relation, they are related using this foreign key. So every time we do something on the corresponding supplier, for example, we delete this supplier row from the supplier database, then the database system will basically check the products database to see if anyone actually references this supplier. And if anyone does, then the action is what we need to define. we can choose to remove the product, or we can choose to sell it to another supplier ID, or we can choose to just set the supplier ID to null. So yeah, that's basically how we can use some foreign keys and primary keys to uh, represent the relationship of our data. And this is precisely why uh, structured or SQL relational databases um, are very commonly used in enterprise because of the underlying business needs that would require us to um, naturally draw out the relationship between each type of data that we have. So to do another example, because we already one-on-one is trivial and one-to-many is already like demoed here. So let's represent a many-to-many relationship. So of course, in real life, there are a lot of different scenarios that we can use. Um, but in this case, let's stick to our e-commerce example. So you have a customer and you have just use the same table. Never mind. So you have customers and you have products, and of course, you can also make like orders. So uh, you have an orders table that stores like each order that you make. And then each order can involve multiple products, as you can visualize from your shipping cart in Shopee or Lazada or whatever. And each product can belong to multiple orders because it can be bought multiple times by multiple different people. So we know that there is a many-to-many relationship between products and orders. So how do we represent this relationship? Because like if you put a foreign key in orders, then it relates to products, then it becomes like a one to many. And similarly, if you put the foreign key to products, it's also just a one to many. But if you put both, then it still doesn't actually work because um, we only have one. If we only have one foreign key for product that references orders, then how do we even given the product, how do we even grab the list of orders that this product is involved in? So um, the solution usually is just to combine one to many relationships. So a many to many relationship is basically just a one. It's basically just a many to one and another many to one combined together. So to further like explain, let's make a table called orders. So this table is basically a bridge or junction table between orders and products. So where do we place the foreign keys? Basically, um, we place both foreign keys into this table. So we have order ID and also product ID. Both are foreign keys that reference their respective tables. Why this works is because basically the relation between orders and orders products is a one-to-many relation, which means an order can have multiple orders products. And similar for relation between products and orders products. So a product can have multiple orders products at the same site. Um, so because of both of this, we know that because of this junction table, we can represent an, many orders having many products because um, this table stores both foreign keys. And every time we want to query something, for example, given a product, what is the list of orders? Then we just do a join. Join will be discussed later, but join is strongly related to foreign keys and primary keys. So using this key, we can do a join between products and orders products. By joining, we get all the order IDs that have the same product ID that we have. And using this order ID, we do another join between orders and orders products and retrieve all the other details in the orders table. For example, the amount spent and uh, the timestamp of the order, and so on. Yep. So this is how we represent uh, different types of relationships using different using foreign keys and primary keys. Yep, it's been quite a while. So I think I'll just maybe make a checkpoint here and maybe does anyone have any questions regarding the concepts that were discussed previously? And you can just feel free to type it in the chat. And then if there's no other questions, then we can move on to the next section. Okay, it seems that no one has any questions yet. So I mean, you can just like privately message if you're shy, but yeah. Let's move on to the next part. So we now dive further into like what are the basic SQL commands that we use. So there are 5 of them basically. Select, from, where, order, limit. Select is basically you retrieve the columns that you specify. So every time we retrieve data, we may not necessarily need all the columns of the data of the table. We only need just a subset of the columns. So we just specify the list of the columns after select. If you want all the columns, you don't need to list all of them. You just need to use a special character called star, which means like all the columns. And from table, basically this is a table name. We can have multiple tables, so we have to specify what table we are referring to. And where condition, it basically filters rows by conditions. For example, the most basic one is I want to retrieve all the customers with this name, all the customers with this last name, all the customers with this unique ID, or all the customers who have spent more than $100, something like this. And for order by, it sorts the results step. So you don't need to do any sorting on your own once data reaches your application, because you can do order by in SQL. And of course, this is also optimized in the underlying implementation of SQL. And there's a limit field which restricts the number of rows written. So if you only want, let's say, the top 10 customers who spend the most money, then you can use order by and then do a limit on 10, limit 10, so you get the top 10 customers. This is also useful for pagination. So for example, if you have you basically have an API, you want your users, you want to limit your results so that you can only return like 10 results every time, but you do a pagination so that like if the user specifies page 1, then you just return top 10 records, then page 2, then return the next 10, and so on. So this is to limit your amount of latency, because let's say you have billions of rows, and it's impossible to send all the rows in an API. It would basically crash the entire server. And so, and the user won't even be able to like read so much data on the client side at once. So what we do is just retrieve uh, a fixed set of data every time the user wants to see it. So this also applies for like infinite scroll that you have. Basically, when you scroll YouTube, you don't load all the videos that are recommended all at once. It's just that you scroll more, then it loads it as you want, as without preloading everything. So limit is very useful here. So we also have to discuss. Maybe we'll do some like demos first. So otherwise, it may be very easy to get lost in like the amount of stuff here. And it's also a bit hard to visualize what actually happens if you use this. Um, so let's say we define an e-commerce database schema in Superbase. So Superbase is basically a platform specifically for PostgreSQL, but it also has like all kinds of support for surrounding the SQL. So, for example, like you can do alerts seamlessly, you can do webhooks and so on. So almost everything is built in. You can even do some like AI stuff, seamlessly integrating to a database. So it provides you like editor visualizers, so you can visualize this database like same as what I drew before. But of course, much better. Um, like it would tell you like what is the table name and what is the column name and what is the like data type of each column. How do these tables relate to each other? What is foreign keys and primary keys? So by just one click, like, anyone can understand what is going on, even for non-technical people. So usually what we run SQL code in editors. So we have an editor here, which this is the code that we use to generate um, our actual database. So apart from the visualizer, you can also see the actual data in and this table editor. You can click into each of these tables. You can see what data is inside. You can even do like dynamic insertions of columns using the GUI. You don't even need to use actual SQL. So Superbase also supports like deployment and so on. So you can seamlessly deploy your database without doing extra stuff with like other vendors. So in my editor, I'll briefly discuss like how does it look like to create schemas and insert data. So as mentioned, we use the keyword create. Create table is also a keyword. Create a table called suppliers, which has the following fields, the following primary key, the following data types, and whether it uh, whether it's required to be not null. If you don't specify it, it's possible for the column to have a value of null. And then we also have this keyword called insert into the table, all this data. And the values are all this values. Uh, so this is values for this first row. As you can see, it's a row based instead of column based paradigm. Everything for needed for first row, everything needed for second row, and so on. And these are all hard coded, of course, but in actual production, if you want to like simulate a large amount of data, um, apart from writing actual SQL, there's an abstraction called ORM. Uh, ORM in your own favorite programming language. For example, Java, JavaScript, TypeScript, Golang, and so on. So, what an ORM does, this is not in the slides. It's basically it is a further abstraction on top of all the SQL operations that you have. So in ORMs, you can just do like db is your ORM object that you initialize. So once you do it, you can just do like db dot insert on insert any or like find one, find many, and so on. So this is much more painless than writing actual SQL because it makes it like extremely easy uh, to specify what you want in your favorite programming language to interact with database. And ORM also handles the connection to your database. and so on. So it stands for object relational mapping. So it maps your object-oriented or object-oriented paradigm in your favorite programming language into a relational paradigm in your database. So with ORMs, you can do easy insertions of your mock data. For example, like you can just do a for loop of random data, for loop of random integers, and just like and then store them into an array and just like db dot insert many. Then you get the equivalent of doing like insert values and all the values they insert. Yeah, so there are two steps of building a database. First is schema, which creates or modifies the tables, schemas, and then the insertion of the actual data. And you can also do like deletion and updates of the data using SQL. And so that's for building the database. So you run the basic queries that we have discussed before. So among all of these queries, all of these keywords, actually there are some are optional. And only the first two are like mandatory to specify. The rest are just like optional. You can just not filter by anything, and you can just not order. You can just not limit. Uh, so let's say, yeah, filtering. The basic things are just like show all the products in details. So if you run this, you highlight this, and then you press the run button. Then it basically gives you all the products and all the customers, all the orders. Yeah. So moving to the next one, which is filtering and sorting. The first one is just that you only want product name and product price from products, and you don't want any other columns. So you uh, run this, and you only get these two columns for all rows. And the next one is that only want this first name, last name, city from customers, and you only want customers who currently stay in New York City. So you do where clause and customer city equals New York. So there's only one entry which satisfies your constraint. And the next one, which is you only want ID, date, and status for orders. And you only want shipped orders. You don't want any other type of orders. So you run this query and you get every order that has been shipped. So it comes very handy in terms of like to it's actually very easy to write for especially for the simple queries. Of course, there are like more complex queries that you will learn. If you've taken CS 2102 before, then actually you don't actually need this workshop. But if you haven't taken, then this is a very good introduction of what to expect in 2102. But 2102 only teaches relational database. It doesn't cover like non-relational database like Redis or MongoDB. So to limit results, it's actually just adding another. This one doesn't have a limit, but it has a descending. So when you show products that have price that is greater than 100, and we order by product price descending. So the highest price comes first, followed by second highest, and so on. We can also sort by ascending. Then the lowest price comes first, and followed by higher prices. And then the next query is for customers. We only want to sort the customers by last name and then first name. Because some customers may have the same last name, so we break ties by the first name. So we just run this, and basically the last name of A comes first, and then B, and so on. And the next query is just to show the first 5 products. Because we don't actually order by anything, so this comes in the order of what we see in the database itself. So the default order without doing any sorting is the order in which we insert the record. So if we insert this record first, then it comes first. Otherwise, it comes second. So and then this one shows the most recent 3 orders. So we order by order date, the descending, which means like orders that are latest should come first, and we limit by the 3 most recent orders. We run this and we get the top 3 recent orders. This is what we have discussed so far. Yeah, so the next one, let's discuss SQL join. So, and basically SQL join is to basically basically connect different tables based on their relationships specified by foreign keys. For example, in what we discussed earlier, suppliers join with products based on the supplier ID foreign keywords on products. And we can also do like multiple joins in the same query. For example, we join products and order products and orders with their respective relationships. So how does the syntax look like? So we have this join keyword. We ignore the inner first, we'll discuss it later. So join what on what. So both of these are tables. Both the from and the inner join customers are table names. And as a short form for all, we can short form for orders, we can just add the variable name for orders, which is O. And customers, we can just use a short form C. And on customer dot O the customer ID, which is the order's customer ID, and C.ID, which is the the customer's ID. So what this does is that it would return for each customer we return a list of the orders the customer has made, because a customer might have made multiple orders, but an order can only be made by exactly one customer. So this is basically the syntax. We specify we specify both tables that we want to join, and then we specify the condition in which we want to join them. Usually it's just like the foreign key equals to the primary key of another table. But it also could be more special kind of conditions that we won't discuss here because they're not actually very commonly used. So the inner or left or right or full keyword can be left, it can be right. Basically what it means is that it's similar to set operations. So if we use inner, which is the default way to join, we have table A and table B. We use inner means that if let's say we specify orders. So for each order O, we join on customer ID equals c.id. So what if we don't find any customers that have the same customer ID as us? Then the entire row will be just dropped in the join result. Because we only take the intersection between A and B and nothing else. So the row will be dropped. But let's say we join on a left join instead of an inner join. So this left refers to the first table that we name here. So what if we do left join? And it's basically everything that is in the intersection and also the left table itself. So for example, we have an order that doesn't have a corresponding customer ID in the customer table, but because of left join, this row is not dropped in the result. It will just be returned. So what happens to other fields in the customer? It will just be null because we don't have a corresponding customer. But if we use inner, then the entire row won't even be in the result because it will be dropped. So for right, it's also the same thing, but right refers to the second table that you specify in your query. So it refers to customers in this case. So it is basically something like it's background. Yeah, it includes the intersection and also the right table. So for example, if a customer doesn't have any orders, the customer would still be inside the join result. But if you use inner, if a customer doesn't have any orders, it'll be excluded from the join result. So that's the thing here. When the usage, and it depends on your use case. For example, if I want to return all customers, even if the customer still doesn't have any order, then you need to use right join instead of inner join. If not, then you want to use inner join. Full basically means like both are inside. So like you draw a Venn diagram, then basically everyone is inside. So for example, like if order doesn't have a corresponding customer or customer doesn't have a corresponding order, then the row would still be inside the result. Just that the next, like for example, order doesn't have a corresponding customer, but the entire row will be in the result, and the c.name itself will be null. So same for if customer doesn't have a corresponding order, then this will still be in the result. It's just that the corresponding O orders, all the ID, all the total, both of these will be null because there's no corresponding report. Yep, so we have just discussed all the different paradigms. We've discussed the 5 different basic commands of how to retrieve data. We've also discussed the join command to combine different tables together. So to put it into use, let's say let's say your boss asks you like, you want to find all the products in the clothing category and list your names and prices. So this not only involves products, it also involves the category table because each product can have only one category, but a category can have multiple products. So category has its own description, which we want. So the way to retrieve it is that we have to do a join between these tables. So this doesn't need to join because we don't need a description. So we just need the product name and price. Then yeah, this query is already enough. Now let's modify this query to actually join the category. So and the category description. So you can just you can try to think like how to modify this query to satisfy the requirement that we want. Yeah, I'll take a small break to drink some water. Maybe 2 minutes of time. And the next query, you can also briefly think of the next query if you have more time. The next query requirements, you want to show all the customers who either live in Los Angeles or Chicago and order the results by last name. So previously we only discussed like how to do like a single condition, for example, larger or equal or something else. But what if you have multiple conditions? And as we have learned uh in any like your 1, 2, 3, 1, there's only some basic conditions. There are only two types, and any other type can be constructed from these two types of multiple conditions. They are basically OR and AND. The OR means that if any of this, if any condition is satisfied, then this will satisfy the entire condition. But for AND, all conditions need to be specified, need to be satisfied for this row to satisfy the entire condition. Otherwise, it would just be omitted from the result. So OR and AND are both keywords in SQL, as we have suspected. Yeah. So this is the other toolbox of keyword that you can use to solve the query. We want either Los Angeles or Chicago. Both of these should satisfy the condition, and we want to order the result by last name. So the table involved is customers. We have a condition, and we also have order by clause to order by last name. Yeah, so you can briefly like write it down on like how you want to. How do you even write a query for this? Yeah. So I'll give a 2-minute break and we'll be back at like 4:08 p.m. Yep. Yeah, let's get back to the discussion. So for the first query, if you want the category description, you want to have one product, we want to do a join, of course, and what kind of join do we need? Because in the schema, if we look at the schema, it's we have a category ID which relates to categories. This is apparently, um, I think it's not actually enforced that the category ID must exist. But in our data, uh, here, customers, uh, orders, the customer ID, order ID, what do we need? All the products. The table we should be looking at is products. So inside products, we have a category ID. So apparently this is like all of it is specified, but it's not a hard requirement that it's not a hard requirement that it should be not at all. So we can just do it. We can just like modify. Okay, there's a referencing record. Basically, this is why like it is much more usable. It's much more UX than other database that like GUI like PGAdmin because category 5 basically it references one of the records, which is sports. So if you click this, then immediately it shows you that the category name is sports. it automatically tells you like what it relates to, which is super cool. But given that we want the category description, category name or description. Let's say just name, and then uh, we want to decide whether we want to do like left or inner join. Left join means like all the products will be included. Inner join means that some products may not be included. So of course it depends on the business requirement, but uh, let's just define like all the products because some products might not fall on any category. So you left join because you want the product in the result, even though it doesn't have a category. So we left join categories on. So we short form the products called P and categories called C, but you can also not short form. So P dot category ID, and you can see that like the whole ID just suggests like the correct column or keywords that you type. So C dot ID, field ID, and basically that's all. We'll run this query. We haven't actually got the C dot ID doesn't exist. It should be C dot category ID dot ID. And the other thing is we haven't specified the category name. T dot product name, T dot product price, category C dot category name, and description. So C dot category description. So once we run this, we can get category ID sent by Chris. Because it could be P dot category ID or C dot category ID, so we have to specify here which one do we need. In the previous query, we don't need to because we only have one table, but now we have two tables. So and both have the same column name, so there's an ambiguity here. So where P dot category ID is among the clothing. But actually, this one you can just like manually go there, identify like what category IDs is this. Once we've done this, we run the query, and we get like okay, this everyone is in category, and also the category name and the category description, which is exactly what we want. So, so yeah, that's how to. First of all, you identify like what tables are involved, whether a join is needed. Then the next step is to you determine what type of join you want. Is it an inner join or left or right join? Usually we only have left join, we have right join because you can just reorder the table and it will be left join. So left join is sufficient. But yeah, usually we just use left or inner or outer in some very rare cases. And then after you determine what kind of join you want, then you write what relates them. Usually it's just a primary key and a foreign key relationship. After you've done this, then you identify like what what constraints or conditions do I need for my data, which is your where clause. Then finally you determine like what is the columns that is actually required because you often don't actually need all columns. And remember to like differentiate between column names, especially it's a good practice to just like if you have multiple tables, then just alias them with some short form, then just like refer to their columns using table dot column name, even though the column name doesn't have an ambiguity in both tables. It's a good practice to immediately read the code and see that this is this column belongs to this table, and this column belongs to the other table, and so on. I think we still have quite a lot of time, so uh, if we still have time, then I would actually like cover more interesting concepts and commands to use. Uh, the next query is show all customers who live in Los Angeles or Chicago and order the results by last name. So we identify the table that we use, which is just customers. We don't need any joins, and the constraint is um, where the location is Los Angeles or the location is equals Chicago. Either one of them is okay. Then we do an order by of the column last name. We don't have an descending requirement, so it's by default it's just ascending. So we have customers, we're a customer city in this. This is an alternative, but the other way to write this is like, our customer city equals Los Angeles or customer city equals Chicago. This way to write this, but because this way of writing is more scalable, like what you write in your usual like programming language, because uh, you have let's say you have 100 cities, then it will be a pain to like write an all clause every time. So and then order by customer last name. By default, it's ascending, so you don't need to specify. But probably a good practice is to just specify whether it's ascending or descending, so that it can be easily seen and we immediately know that it's ascending. So the last example is you want to list the orders placed on 2024 January 15, including the order ID, customer ID, and order status. This doesn't seem to actually need other tables other than order because if you look at the query, it's just pretty simple. If you want, if I add a requirement, say that I want customer, you need a join, which is actually similar as the first query. So I'll just leave it as an exercise for you to do. I think I'll just share this schema, share share all the queries later. But maybe I'll share it now in the chat. Uh, but I'll also share later. Exceeds the amount of words. So you can only do like a text file. So let's see. Uh, replace this with it. And we can attach it as a file. So this is a schema. You just need to copy paste. You need a Superbase account. So just like sign up, enter. And the other thing you need is like the list of commands, at least like examples and exercises. Make another file. And then you have examples the SQL. So you just copy paste both of this and paste it into the editor. Then you can play around with it. Okay, so you're done with the example. Actually, there's another example called actual customer order ID, customer first name, and customer last name for each one. This is actually like similar because like it needs like both tables. So we need to do like join. So actually both queries are like similar in nature. So you need an inner join of orders and customers. I'll show the product and supplier name of each product. Because the supplier name is only available on the supplier table, so you need to do a join between products and suppliers. Uh, each product has exactly one supply or zero. Uh, so we can do an inner join and just list out product name and also supplier. It's also pretty easy. Yeah, so now we have discussed to give a brief recap of what we discussed up to now. We discussed what is a database, and what is an RDBMS, what is a SID, what is other types of uh, DBMS, for example, NoSQL, graph database, vector database, columnar database, key value database, and so on. And we also discussed OLTP and OLIP as two main different use cases of the databases. OLTP is mainly for live applications, um, like e-commerce, social media, uh, some website they use that needs like backend, like needs user authentication as well, that enables the user to modify the data concurrently at the same time, potential lot of users. And OLAP, which is mostly not many users, maybe just you, but use cases for data science, machine learning, where you have to ingest and load a huge amount of data. So we also discussed why do we need SQL, what is SQL, and what are the basic commands of SQL, what is a schema, what is a PK, primary key, and the FK, foreign key, the basic SQL commands, joins in SQL. Yeah. So this is what we have discussed. Uh, we still have half an hour, and we only have index to cover. So I will introduce another concept, which is grouping. Grouping and aggregation in SQL, which is also a very useful concept. But let's cover indexes. So what actually is an index, and why is it so powerful in database optimization? Uh, an index is a data structure that speeds up lookups in a column. So we can use a B tree or hash table as what you have learned in 2040S. Uh, the B tree is basically a very special tree, a very special search tree. It's not binary. It's not binary search tree, and it's also not like exactly like a search tree, but it organizes data in a way that is extremely efficient for indexes. And the hash table is basically just um, you have a key value pairs. And, you can easily keep track of. So B trees is usually used for um, things that need an ordering because it keeps track of orderings. And how a B tree look like is just like basically like there's a root and there's like all the nodes that come out from this root. Basically, and then we have other nodes and then so on and so forth, all the way down into there's something called pages. The pages is basically the text file that you store all your data. So this pages are basically on disk, which is why if you don't use any index, then it could possibly be very slow because you have to scan all these disk pages. And if you have index, let's say the query is something like, um, I want the list of customers who has spent around $100 and maybe $90. So if you have an index on the amount spent by the customer, then we index on this, then your tree is basically about this value. So everyone that has like lower amount is in. Maybe this page is like 0 to 20, 20 to 40, and so on. So all these pages will be skipped because if you traverse from the top, uh, conceptually is similar as any search tree, like binary search tree. Like you have like, okay, everyone is below 20 is here, everyone is below 40 is here, below 60. So between this, you have a edge leading to a new node, and next edge leading another new node, and each node has its own ranges, and you can further dive down all the way until you meet your this page. Because of this B tree, we only need to traverse maybe the last two, only the last this page, which has 90, which is like 80 to 100. This is a bit of a simplification, but basically it's how it works. So B trees can help with are very helpful with um, column values that have some kind of ordering. So it helps in because you want to range query and you reduce the amount of queries that you need, the amount of disk operations that you need. And this doesn't seem to like improve a lot, but actually it improves much more than just it eliminates much more operations than imagine because if a database has like customers spend up to like $1 million, then of course you only want a small range, then of course the speed up will be like up to like 100x speed up, something like this. Then it's very significant. Then another paradigm to do like indexing is hash table. Then it's not very helpful with range queries or some kind of ordering. Queries that need some kind of ordering. But it is very helpful if like if you want to do like exact queries. For example, get a list of customers who spend exactly $80, then the hash table will just like, if you have a hash on amount spent, then you have a key value pair. The key is like 80 that leads to like the other values. And it also greatly reduces the amount of like, these pages that you have to scan. Because like it might be an oversimplification. So in reality, as we actually implement hash tables in real life, in like programming languages, we do a modular of we have a very good hash function that can distribute the data very evenly, relatively. Then let's say it's called H. Then let's say H can be anything, but let's say you use modular. And if strings, then we use more complex hashing algorithms to make sure that everything is like relatively is evenly distributed. Then it becomes like everyone that has keys between 80 to 100 is maybe in this bucket, and the other guy that has like 60 to 80, everyone else is in this bucket and so on. So only have to traverse every this page that is inside this bucket. Then it also saves a lot of space. Because 80, then we just divide, you jump in this bucket. It has to be in this bucket only. So it helps us save a lot of space, a lot of disk queries. So this for hash table. So basically an index is a data structure that speeds up the lookups for us by greatly reducing the amount of disk that we have to access. It is created by using create index. Then we name the index column on table. Now the column. So this index column is a new thing. But the column is like the column that we need to add this index on. And by default, foreign keys and primary keys are indexed already. And usually it's indexed by B-tree. Because every time we do joins, we need to use PKs or FKs. And having them on by default on index is very important because it speeds up joins. Because, for example, we have an index on customer ID, and we have an index in product ID, and maybe like the foreign key that connects like product to customer. So if you do like a left join of like customer and product, for each customer, what are the list of products that he or she has bought? Then we can leverage on this index on the foreign and primary key because let's say the ID is like two. Like we have a list of customer IDs, 2, 3, 4, and so on. Da, da, da. And then for ID2, and then we also have the foreign key on product. So because of any hash or B-tree indexes, we can very efficiently identify the disk pages of customer that is that has an ID of 2. And for joint algorithms, there are a lot of joint algorithms. And which algorithm gets chosen is dependent on the database own decision. Because there can be multiple indexes and there can even be indexes on multiple columns all at once. For example, index on A and index on B, like AB as a whole. So what it means is like it orders by A, and if A is the same, then ordered by B, and so on. So database will determine like how many records are on each side, and basically estimate like what is the complexity of like if you use this index and what is the complexity of using another index, and it would make a decision and use the algorithm that has the lowest complexity. So what is the trade-off adding indexes? Why not just add index on every column, every single column? The problem is that the process that is faster for select and join operations. But the con is like every time you insert something, you have to update an entire index. That all the indexes that you have made. So it makes it very inefficient in terms of like write performance. Like if you write a new row, then you have to like redo all your index. Then it becomes slow of due to index maintenance and extra storage. So only index rows and only index columns that actually you actually going to commonly use. For example, primary key and foreign key is a must, so it's done by default. But there are definitely some columns that are used more commonly than others. And especially like let's say you want to do joins, then columns that are involved in the join are important. If you want to do like select, if you want to do like ordering, then the column that is being ordered on is of course you want to index it because it helps in doing ordering and sorting. And also like columns that you want to do like where conditions because it's also very important and you can easily use it um, to leverage on it and reduce your number of queries on these pages. So we introduced PostgreSQL, which is actually what we used just now in Supabase. Underlying is just Postgres. It's just a wrapper on uh, a glorified wrapper on Postgres, but it's very useful because of the sheer amount of stuff that you can do with this wrapper. For example, like real time, like you can just like if anyone adds a row, then you can run like a real time listening. Or if this guy adds a row, then it triggers some function in JavaScript to do something else. They'll be very useful for let's say you want to implement a chat room and someone adds a message and you want to like notify everyone, you want to subscribe to this, then that's useful. Of course, like deployment is smooth and authentication is also like quite smooth. And other ways you can use Postgres is either you download the whole package. But for Mac, it's just like to install Postgres. For other like OS, it's like basically like sudo apt-get or some stuff. But it's usually very easy to figure out. And and the other way is use Docker. I wouldn't further like explain what is Docker because you're probably going to learn it somewhere else in the workshops. What it does is basically if you have Docker, then it's basically like cross-platform consistency because uh, you just run Docker as a container, then the container can work on any OS, so it eliminates any problem, any OS, any OS version, any software versions. So it eliminates all problems of compatibility because you might install a whole Postgres on your own PC, then you realize that it doesn't work because of some other issues of compatibility. So Docker basically you just need to you need to pull the Docker image. So for a lot of like major softwares, like Postgres or Redis or some other software, they have an official Docker image. So you just have to pull Postgres, pull the image onto your PC. Then you want to run this image in a container. Uh, so in the containers, so these are all the containers that I have. We're going to run it again. So just do this. And we're going to run if a command saying docker run. I name this container called my Postgres. I specify my Postgres password to be your own password, and this P mapping is basically like port. So PostgreSQL by default uh, runs on the port of 5432. Uh, so like a port basically in your own PC has its own process that is running. For example, if you just localhost a Node.js server, then by default it runs on port 8000. Of course, you can also adjust the port according to your needs. So 5432 means that uh, this Postgres will be launched on port 5432 inside Docker, and it will map to 543 port 5432 in my own machine. So that's why in my machine I can access it. Otherwise, I won't be able to access it because the thing is running in a Docker container, and I can't like using my PC. I can't really like connect directly to the container unless there's like a binding, which is specified here, and just run the whole thing. Yeah. So it's actually not up, and you can look at all the static frames. For example, listening on 5432. So so once the server is up, and once you can connect to it using the port of 5432 in your favorite programming language. And usually using ORM can connect to this endpoint, this port, and manage the connection on its own. So yeah, that's basically how you set up a Postgres. You can either install it natively, or you can use a Docker container. And there are several options to visualize and operate on the data. You can use pgadmin, which is a very common GUI to use PostgreSQL. And you can also use uh, this this GUI called dbeaver, which I think is even more versatile because not just Postgres, it also supports like other types of databases like anything else like DuckDB, so DuckDB, everything, ClickHouse, all the major open source and closed source databases. So it helps you visualize and helps you like run editors on the data. So that's it. And of course, we discussed like why Postgres is so popular. It's because it has a long history already as a advanced and enterprise class relational database. It was developed since 1986 at Berkeley. It's actually open source with a strong community behind it. And it supports all the basic SQL features. And also has like a lot of extensions, for example, PostGIS, geospatial data, because like you want to store like latitude and longitude, and it makes it more efficient for you to store it. And you can even like visualize the entire map, not just that long, but also like how it looks like in real world, sort of like Google Maps. Then it's actually used in a lot of tech companies like Apple, Instagram, Reddit, and others. For this, I already done it in Superbase. So we just um, so basically we covered like uh, everything that we want to cover. But let's get some like bonus like introduction. So another concept I want to intro is group by concept, because group by is a keyword also, and what it does is like it groups data by columns. For example, uh, in my table, I want to group like customers by maybe their city. So everyone in Los Angeles should be maybe state, because like we have like San Diego, San Fran for California. So let's say we want to group them by state, and then this enables us to do a lot of more advanced and useful queries. For example, I want to find out how many customers in California do I have, or like how many customers in NY do I have. This will not be possible with the current paradigm. It will still be possible. Like you can just do like you can just do a where clause where customer state equals CA, but But what if I ask you to just do this summation of customers in each and every state that we have? Then you have to do like 55 queries for if 50 queries for the US. Then yeah, then it's really quite long. And you can also we can also ask you to do like aggregations that not just summation, like minimum, maximum, uh, mean, standard deviation, median, and so on. So to simplify this, the other operation that we have is group by. So let's say group by, we want to group what is number of customers in each state. So only customers table is involved in this case. So we can do so some is also keyword. Some custom we can do like um, some star because like if it's a row then it counts as one. Uh, usually sum is on columns. We want to sum a specific column, but now we just want to count rows, so we use the count keyword, which star, which means like how many, like if. So we select our star from the uh, we want to group by the column which is customer state. That's it basically. If you run this, yeah, this count, but you can just rename this column as customer count. Run it. Run this customer count equals so yeah, this is basically it. We don't we don't include states that are like not present in the data right now. So this is why like group by is very useful. We can also do like max of something else like amount spent or something. Give you an idea. Max mean standard deviation of, of a particular data of each column that we group by. And of course, group by can also be used together with join as well. And another thing is there's a having also. And it is basically like where. It's basically like where, but the difference here is that because customer count is an aggregation, and we can't really do like where customer is larger than where customer count is larger than let's say 2. Because at this point in time in the evaluation, we still don't have customer count. So having is the keyword that helps us filter based on the aggregation result that we have for each group. Because if you use where clause, it is only applied on all the columns that we have before we do the aggregation. So they serve different purposes. So you only want customer count that is larger than 2. Customer count does not exist. I think at this point we can't really do an alias. We need to do that exactly. Run this. Run this. Here we get all the rows that has customer count that is larger than 2 only. The rest are left out. So this is basically grouped by in SQL. So I think we have covered everything that we want to cover plus some extra info in this workshop. Hopefully, that would help you get started with like how to build your own database for your orbital project. Yeah. And in the next session, we'll cover other types of database. For example, we only cover two as a demo, which is MongoDB and Redis. Redis is a key value store, and MongoDB is a document store. So the difference here is that we don't really have like very strong types of constraints in MongoDB. We don't have primary keys and foreign keys in MongoDB. And for Redis, it's totally different because we only have keys and values, and nothing else. So the key is very important. So the use case is different is that if you want to decide which one to use for the project. So if your data is like very relational, they have a lot of relationships and actually the representation is very important. Then you want to use SQL. And one of the SQL like database management systems that you can use is Postgres. But of course, you can also use other open source alternatives like MySQL. Usually, people just use open source because it is totally free, and you can. But if you use closed source like Oracle or something like Microsoft SQL, then you have to pay, which might not even be worth it. Uh, then if your data is less structured, less relations, then you want to choose MongoDB because it's not limited by the constraint of all these relationships. But we'll discuss it further. For example, like how to organize, how do you even design a schema in MongoDB if you don't have any foreign keys? For example, in this case, which kind of reflects the advantage of using a relational database because let's say orders and products. If it's MongoDB, you don't have foreign key, then maybe you store a copy of all the products under each order in the order database. Then you store a list of orders for the product in the product database. Then you have to like duplicate the data. Well, in relational SQL, it's just you only store each item once. You don't need to duplicate it in another table. But by Mongo, you have to do this. And every time you update something, you have to update in both tables. So, but the advantage is that you don't have to do joins. You can just immediately retrieve the data. So it helps for if your application is much more reliant on reads than writes, which means your users don't update the data that often. Then you want to use MongoDB so that you can easily retrieve the data without additional complex joins. But if you have more rights from the users, then maybe you want to consider using PostgreSQL. But it's not very clear cut because, of course, even if you use Mongo, there are ways to. It can also be slow, and even if you use SQL, it doesn't necessarily mean that your write performance would be better or worse. It depends on how you organize the data. But that's just the general rule of thumb. And Redis is mainly used for like cache, or if you want to use vector database, you consider using Redis, especially if you want to do like some LLM stuff like agentic MCPs and so on. Then it can be good. And Redis can also be used um, for use as a message queue, a simple message queue. Can also be used for doing pub sub. For example, you want to do like chat group, then you have pub sub, which means like if someone inserts a key value pair into Redis, then they are more like uh, basically it would alert you if you subscribe to for this subject. Yeah, and basically that's the overview. Yeah. Does anyone have any questions? Yeah, I think I missed out on the additional concept of like how people usually store data if they have like a large amount of records. So in MongoDB, there's this concept called sharding, which means like because in Mongo it's still mandatory for each table to have a prime a primary key, like a unique identifier. So if we have a lot of data and we don't want to store them all in just one table, we want to split the multiple tables for, for the same schema. And actually Mongo doesn't have a schema. You can just insert anything you want in the same table, it won't complain. But what we do is like we have a hash function for the unique ID. Usually it's just modulo based, and you just like, distribute okay, everyone who has modulo. That's why we have like four different databases, different tables that we want to store the same data. Then it's just like everyone that has modulos will be in this server, this table. Then everyone has modulo one is in another server. So yeah, this will help distribute the load. And even when we do queries involving unique IDs, then we can just like, split the traffic to this server because we know that the modulo of this unique ID is 0. Then it helps. Reason we can't do this in SQL is because uh, we have other fields in SQL. Then if you just split by using primary key, then uh, what if I want to query like not by primary key but by other columns? Then you have to split the traffic to other servers as well. You know, do queries on everyone. Then you merge the result together in your own like, parent server. Then it's like it's pointless to do this because you you waste network bandwidth by doing network requests to other servers. Then you again use some waste some CPU time by combining the results. But for Mongo, we don't usually need to like filter using oh, any other key other than the unique identifier. So there's a difference in use case. Yeah, I think we have only 3 minutes left, and if you don't have any other questions, then I think we can end it here. I'm not sure whether we need like attendance taking. Uh, if if yes, then actually I have a form. Yeah, I would share the slides and both of these files for schema and example on the canvas, and that's all. See you all next week, Saturday at 10 a.m.